Cloud computing would not be possible if not for virtual machines. They are the fundamental resource for cloud-native applications. Then along came Docker with its containers, and the virtualization scene got a bit more complicated and confusing. So, we kicked off a new series where we go deep on virtual machines and containers, aiming to clear up any confusion between these important technologies. In episode 81 of Mobycast, we discussed full virtualization, also known as virtual machines. We explained hypervisors, the fundamental technology that enables virtual machines. And then we took a detailed look at how Type 1 hypervisors work. In today's episode of Mobycast, Jon and Chris bring these concepts to life by examining several popular hypervisor implementations. Welcome to Mobycast, a show about the techniques and technologies used by the best cloud-native software teams. Each week, your hosts Jon Christensen and Chris Hickman pick a software concept and dive deep to figure it out.
Before we get started today, I'm so happy and so proud to be able to announce that we have a sponsor. So Mobycast is no longer ad-free. But our sponsor is one that we really do care about. We use Circle CI, and we've talked about Circle CI in a previous episode. I'll link to it in the show notes. So I just have this to say. This episode is brought to you by Circle CI, the continuous integration and delivery service used by companies like Twilio, Intuit, and Tinder. CI/CD is so important for keeping teams building. It's all Circle CI does. They focus on creating powerful, flexible CI/CD pipelines so that you and your team can focus on doing what you do best. Whether you're a company of 5 or 500, Circle CI can build, test, and deploy your Linux, Windows, and Mac OS projects from GitHub and Bitbucket in their cloud or installed on your servers. And anyone can sign up and start building for free, since Circle CI gives both private and public projects 1,000 free build minutes per month. Sign up and start building for free at circleci.com. Welcome, Chris. It's another episode of Mobycast.
Hey, Jon. It's good to be back.
Hey, good to have you back. So, we're here without Rich. We've started a new sort of progression with a new producer, and it's just going to be you and I from now on. But I think we still like to talk about what we're up to and just give our listeners a little bit more than talking robots that know about software. So what have you been up to, Chris?
So we you know me, I'm a cycling nut. This year, my goal has been to have 4,000 miles.
That is not short.
On my bike? No, it's not. It's a tough one. I had a kind of delay to my season where I didn't get too much in January through April. So I'm kind of playing catch up. I have passed 3,000 miles. I'm glad about that. But the thing that I've noticed recently is that because of the weather here, and we're now into September, the weather has not been as conducive. So I'm taking a bit more rest days. And what I've noticed is that rest days are actually very conducive to KOMs.
Oh, yeah, they are.
So lately it's been kind of fun doing these rides and getting a KOM almost every time. And, some of them are pretty meaningless, but some of them are like, first out of like 1,500 people. And those are good ones. Yeah. So I'm enjoying my crowns.
Excellent. Yeah, congrats on that. That's really cool.
Thanks.
And over here, I've also been, you're listening to this in October, I think, but here it is. We're recording it in September, and I'm just getting ready to go on a trip that I do every year, either in September or October, to go visit some friends in Baja California, do some surfing. This year on the trip, there'll be another software person, Matt Morey. Hope he's listening right now. He is the VP of technology for a company called Valtech. And, excellent person. And he really got his, he started doing software, really deeply into mobile stuff. He wrote a book about doing core data in iOS that was excellent. And that's how I got to know him, was when he presented that book at a meeting in San Diego. And turns out we both surf. So we've been friends ever since. I'm looking forward to that. I'm leaving later this afternoon to go catch my plane.
Sounds like fun.
Yeah, it'll be great. So let's go back to revisiting our episode 1 on virtual machines versus containers. Last week we talked a lot about virtual machines, and we started getting into hypervisors, and it started getting pretty deep. And I had so many questions about hypervisors that I couldn't ask because we didn't have enough time to get into it. But this week I don't even need to ask those questions because we're all prepared to talk a bunch about hypervisor implementations this week. So Chris, you want to kick us off?
Yeah. So, just again, as a quick refresher, last episode was all about full virtualization, aka virtual machines, and really how hypervisors enable virtual machines. And there's two types of hypervisors, type 1, type 2. Type 2 run in user space. Type 1 is running directly against the hardware, and think of them as their own an operating system in and of itself, right? So type 1 hypervisors are really what allows for performance and scale. It's what's being used in any kind of data center and definitely in the cloud. And so that's something that we'll be focusing on. So we talked about just how type 1 hypervisors work in general and kind of like the theory behind it. And so today, hopefully, we'll kind of bring those concepts to life by actually looking at several different hypervisor implementations and how they work to
Excellent.
Kind of maybe just bring all that stuff together.
Cool.
Right. So two hypervisor implementations to talk about today. One is Hyper-V, which is a type 1 hypervisor from Microsoft. And then we'll also talk a bit about KVM, which is a type 1 hypervisor primarily for Linux, although it's been ported to other operating systems as well. But those are two very, very popular hypervisors out there right now that will being used in the cloud, and we'll dive into those. So why don't we start with hypervisor, the Microsoft's hypervisor Hyper-V.
And we mentioned Hyper-V last week, and I remember we even got off the rails a little bit because I was like, oh wait, can your everyday user operating system just be a virtual machine, and Hyper-V just gets scripted to start that? And we decided no, that wouldn't make any sense, because why would you want to add that extra processing and extra wait time when it's just you and your machine? So yeah, let's find out how Hyper-V actually works. And obviously it's for data centers and not for your own personal machines.
Right. Yeah. So hypervisor, Hyper-V.
You want to call it hypervisor
know, yeah.
V. It's hypervisor V. No, it's Hyper-V.
I mean, engineers, we're so it's kind of like the same problem with in astronomy, right? It's like, how do you name things? It's such a hard problem. And so you name astronomical objects with, serial numbers essentially. And then here we are in the software world, and we say things like, we have a hypervisor, which is basically the supervisor of the supervisor. So hypervisor, we have a hypervisor product called Hyper-V, and we have there's two types of hypervisors, and what do we call them? Type 1, type 2, right? So
it's purely a mnemonic device. It's always easy to remember what 1 and 2 means and what the difference is. It's built into the net.
Nothing but alphabet soup.
Yes.
Yeah. So Hyper-V, Microsoft's type 1 hypervisor, and it's part of Windows Server itself. You install it. You can install it after the fact, right? After Windows Server install, you can install this as a role. There's various other ways of installing it, but it's something that's it's kind of there, but you have to enable it. There's also separate standalone installs as well for kind of I think more bare metal type type circumstances and whatnot. But so with Hyper-V, it has this concept of partitions. And so the virtual machines are isolated inside these partitions, and these partitions are essentially their logical units of isolation. And what's kind of interesting with Hyper-V is that there's parent partitions and child partitions.
Okay.
And the parent partition is pretty pretty important, just by virtue of its name, right? So that's where that's where the actual virtualization software is going to run. So basically the Hyper-V functionality itself is going to be running in that parent partition, and it's the one that has the direct access to the hardware.
So yeah, let me actually stop you for a second, because whenever I hear about something being partitioned, it's that thing. Like, what is being partitioned? The memory, the amount of time you get access to running instructions on the CPU. Like, what's being partitioned?
So in this particular case, you can think of it as you can kind of think of it as a VM in and of itself, and so it's partitioning
the computer.
What a VM partitions, right? So,
okay.
But this is also like the controller for all the guest OSs that may run on this machine as well, right? So,
I think it is fair to say it's kind of partitioning the computer and all that encompasses. Like, I've got a computer. A computer means so many things. It means running instructions. It means memory. It means network. It means, sending stuff to a screen. It means I/O. It means everything. And I think that's maybe why they're using that word partition. I'm partitioning up this hardware.
Yeah, I mean, I suppose, the other way of thinking of it is that you can think of each virtual machine runs in a partition. So
you see why I'm so insistent on this? Like, partition doesn't mean anything without the thing it partitions.
Right.
That's kind of a critical part of the definition of the word.
Right.
So that's why I can't let go of it. And for lack of a better thing, it's like the computer. Like, you're partitioning the computer.
Yeah. So partitions are basically, it's the user mode software. It's where guest OSs run, and it turns out like this is where the kind of the management, the virtualization software that Hyper-V needs in order to deal with these guest OSs, that it's where that lives. So there still is the hypervisor itself. It's running in a privilege ring, and you still have the operating system kernel, but there's these partitions, and there's one special partition. It's the parent partition, and that is where the virtual machine management service lives. That's where is kind of like the management tasks that the hypervisor would need to do, right, for a system like this. Okay. And this is not a unique architecture. The Zen hypervisor system kind of has a similar concept. Instead of partitions, they call them domains, and there's a special domain 0 that essentially is their concept of a parent partition. And then they have user domains, and those are the guest OSs. They run in those domains. And so likewise, Hyper-V has, they've called them partitions.
Okay.
Right. So again, the parent partition, this is where the virtualization software runs, and it also has direct access to the hardware. There needs to be at least one parent partition, and it needs to be running a supported version of Windows Server, right? Which kind of makes sense. Like the code is written for Windows Server, so inside that partition should be running Windows Server. And so the parent partition is responsible for creating child partitions, which then host the guest OSs, right? So when you're spinning up your VMs, it's the parent partition that's responsible for creating those child partitions.
Okay.
And that's done via Hyper-V's hypercall API.
Okay.
Right? The parent partitions also run something called the VSP, which is the virtualization service provider. And that connects to another component, which is the VM bus. And the VM bus is basically, it's the logical channel which enables inter-partition communication. Right? So you can think of it, this is just the communication channel, this VM bus. And so when child partitions have device access requests, it's going through the VM bus to the VSP, and then accessing the hardware, right? And,
tell me again what the VSP is.
That's the virtualization service provider.
Okay.
Right. So it's
I get the bus was actually easy. I was like, okay, I understand this bus. That's where all these, where I'm going to talk to the hardware. I'm going to put the messages are going to go on the bus. But the VSP, I was like, what is that?
So the VSP, so virtualization service provider. So basically, I think that is the part of the hypervisor functionality that is providing that the virtualized hardware as services, right? Okay.
So I'm a child partition. Instead of talking to the hardware, I'm talking to my VSP. The VSP is then responsible for putting stuff on the VM bus, and the VM bus is what kind of shuffles information back and forth between my actual hardware and my VSP. Yeah,
maybe it's slight nuance. The VM bus is for inter-partition communication. Right. And so it's the parent partition, I believe. But
why do partitions need to talk to each other? So I've got two child partitions. They shouldn't need to ever talk to each other.
They need to talk to the parent partition, right? So this is the architecture of Hyper-V, right? So that's
okay.
So I don't think like there's.
I wouldn't think that they're going
to be talking to each other, right? They shouldn't even know that those other guest OSs are running on that machine.
Right. If they are talking to each other, they're talking to each other through established ways of computers talking to one another, like networking.
Mm-hmm. But they are talking to the parent, right? So
okay.
And so
and the thing they're doing to talk to the parent is basically saying, I'm just trying to understand that too. Like the parent is kind of a virtual machine. It's a partition, but you're saying it's running Windows Server, and the child partitions are like, hey parent, shutting down, or hey parent, what else do they need to tell the parent? What kinds of things do the children need to tell the parent? Do you know?
Well, it's like device access requests, right? So whenever they need to access hardware, right, that's a request that goes onto the bus.
Okay, and the parent handles that?
Mm-hmm. So the parent handles that through the VSP, and then that then goes into through the VSP to access the hardware, and then the whole thing is remapped, right, and back onto the bus.
So, but that is a little surprising to me because that sounds like maybe para-virtualization, which we discussed last week, and not full-on hardware virtualization. Because if I've got to talk to an operating system to talk to my hardware instead of just kind of being handed access to the operating system, it doesn't feel like hardware virtualization.
So there's a whole bunch of like mix and match here and kind of blending of boundaries. So by virtue of having like a hypercall API, that definitely is borrowing a bit on para-virtualization and how that works. But it also uses hardware virtualization specific, again, the chip specific functionality. So like, whether it be for dealing with memory pages and page table virtualization or actual CPU instructions that help out with this. So that's being taken advantage of as well with it. So I guess, without going into like the really deep details of how Hyper-V is actually architected and written, because we'll just get lost in the weeds and we'll actually run up against we need to go talk to someone actually that wrote the code. Right. But so this is more of a logical architecture of just kind of like keeping it at the point that like it is very performant. It is leveraging hardware virtualization, again, through CPU instructions, as well as things like with page table virtualization support that like the Intel and the AMD chips provide. It's using this bus to kind of deal with those kinds of calls, and the emulation is kept to a minimum, right? It's leveraging direct hardware access where possible. It doesn't require any guest OS modifications, right? Which is kind of like para-virtualization. That's one of the big requirements there, is that the guest OS has to be aware of it.
Yeah, I think that one of the things that would help me understand, and I don't think we're ready to answer this, but I think one of the things that would help me understand this is like that VSP communication and that bus that happens. Like, I want to know whether that kind of like there's a bunch of sort of machine startup communication that happens. Like, hey, I'm a virtual machine. I need some memory. I need some network. I need some, other things. VSP, get them for me. And then the VSP is like, all right, bus, over to the parent operating system. The parent operating system is like, here you go. Here's all the things you asked for. Now talk to them directly. Or whether it's always like, hey, I need this memory address, VSP, bus. And parent operating system's like, here's what's at this memory address. Like that seems to me to be going through a lot of layers versus like, what if this whole architecture could just be like a way of kind of getting the child partition set up and talking to its hardware directly, and kind of be like, all right, let me know if you need a change. From here on, you're talking. I'm going to make sure you only talk to the part you're allowed to talk to, but beyond that, like you are pretty much talking to the metal. I would like to understand that. Like that, I think that would help me get my head around this. Like whether it's a kind of a handshake or whether it's a constant chatty communication through this VSP and bus.
Mm-hmm. Yeah, just a few additional points here on the child partitions. So they don't have the direct access to the hardware. They have a virtual view of the processor, and they run in a guest virtual address space,
okay,
which is obviously not necessarily the entire virtual address space. The hypervisor is handling the interrupts to the processor, and it's redirecting those to whatever partition should be receiving it, right? And then any requests to virtual devices, those are redirected to the VM bus, to the devices in the parent partition. Right. So
it sounds like it is more likely to be kind of the latter. Like it's not setting you up and being like, all right, you're kind of like level 0 access to the hardware from here on. It's more like you talk to me when you need something. You talk to this VSP, and I'm the parent. For anything, you have to go through me.
For devices, for sure, it's going along the VM bus. And then so again, that's one of the roles of the parent partition is to create the child partitions. And so basically by doing that, right, it is setting up things like, okay, what's your memory space, what's your CPU, all that stuff that involves with instantiating a new VM for a guest OS. And then after that, it's like, okay, how do you deal with devices? How do you deal with the processor? And so it's a blend here, right, of all that, kind of finding the right balance between performance and not needing guest OS modifications. Where can we leverage hardware virtualization and actual support on the chip versus what stuff's going to be done in software?
Cool.
And so the good thing here is that like not a lot is being emulated. It really is running on the hardware. And there is some messaging going back and forth. But again, that's pretty much optimized.
Cool. Yeah, let's continue. I sort of have this other like bigger question, but I want to see if it gets answered by continuing on and talking about another hypervisor.
Sure. So let's talk about KVM. So KVM stands for kernel-based virtual machine. And this is a virtualization module in the actual Linux kernel. So what it does is it turns the Linux kernel itself into a hypervisor. So this is a little bit of, again, a blend, right? We talked about in the previous episode, type 1, type 2 hypervisors, where type 1 hypervisors really, for the most part, you think of them as an operating system in and of itself. The only reason why they exist is to be installed onto, bare metal, and then they exist to just run virtual machines, right? So to create them, to manage them, to delete them and whatnot.
But this is so huge for me. I think you already just answered my bigger question. So let me just try to explain what's going on in my head. I was trying to figure out about when it comes to partitioning a processor and like splitting it up. A big part of splitting it up is basically giving different processes access to run their instructions. Because that's the job of a processor, right? Like here's if you go all the way back to like early computers, they're very simple. It's like, here's a place of memory, it's got some instructions, run through those things and do them as fast as you can. and like go get it, the next instruction, next instruction, next instruction. And each instruction may require you to put a little bit of information into a register or retrieve information from a register, or like go all the way out to memory and get some information from there and do something with it. And then like the point of an operating system, like one of the major points of an operating system is to say, hey, we're not just going to run programs one at a time anymore. We're going to have many processes running at once. And so we're going to make this thing that's smart about that. And it's able to just sort of say, now you, and like pick which process runs, and gets access to the operating system. And the processes have priorities, and they maybe have blocks of things where it's like, you cannot interrupt this process during this block. And all that kind of stuff like that. Also, it just sort of makes core sense, and it's been something that I've known for many years. And there could be nuances that I don't understand, but at least it makes a logical sense in my mind. So I was like, well, if we have virtual machines, and they each think of themselves as, a whole computer, then they're not going to be that good at playing nice when it comes to a processor. Like, they're not going to be that good at being like, oh, I'll only do a few executions and then I'm going to give someone else a turn. They're going to want to just do what they do, which is run instructions. So I was like, how does a hypervisor manage that? How does it deal with lots of virtual machines running on the same hardware? And I was like thinking about how does this have anything to do with the number of cores on the machine? How does it have anything to do with, and like how does the processor level virtualization work? Like, what is it offering up? Is it offering up little partitions of execution time? Like, oh, you get 5 instructions, or you get 500 instructions, or, I don't know the number, but like, you see what I mean? Like, how is it partitioning up? It's essentially instruction execution time. And what you just told me, I'm sorry, this is so long-winded, but what you just told me, it answers that question. You said that the virtualization module is essentially itself a little Linux kernel, which is like, aha. Guess what Linux kernels are really good at? They're really good at giving processes a little time to run on a CPU. Like, that's literally the most important thing that a Linux kernel does. So now it's like, oh yeah, each virtual machine can sort of become a process for this Linux kernel to manage and give each one some time to get some instructions executed. And that may be wrong, but it feels intuitively right to me.
Yeah, and I think, again, I mean, these are pretty deep technical concepts, and it can be kind of hard to wrap your brain around it. So, we talked about with Hyper-V, like the hypervisor handles the interrupts to the processor, right, and is redirecting it to the respective partition, right? So that's kind of gives you hints on like how. Right,
but when you say it that technically, it's like, I'm not sure what you said. But now that I just had my little aha moment, I'm like, oh yeah, yes, that makes sense.
Right. Yeah, just keep in mind that, so we're talking about KVM now. This is just one way of doing it, right? So this is the way that KVM came to life, was a
bunch of engineers sitting around going, oh, we already have this thing that can manage processes. Let's see if we can use it to manage virtual machine.
Right. So they said, we can write this new kernel module that basically implements hypervisor functionality, and that's how we're going to do virtualization on Linux, right? Which is, before the KVM, there was Zen, and Zen does it different. Zen does it more along the lines of what Hyper-V, the architecture that Hyper-V has, right? But kind of, again, same, they're both type 1 hypervisors. The different ways that they went about implementing it. At the end of the day, though, the same core things are happening, right? So we talked about how hypervisor, so kernel is also known as a supervisor, right? And we said that a hypervisor came about because it's really the supervisor of the supervisors. Right. So it's kind of, so what you're talking about, like, oh, the kernel is responsible for, allocating CPU resources and who gets to run when, and dealing with interrupts and the devices and all that kind of stuff, right? So the same thing, hypervisor is involved with that as well. It's just across multiples of these things. And so just where is that implemented is just going to depend on the, whatever implementation you're talking about and how it's done. But the principles are there.
Yeah. I'm so many more things are coming to my mind now. Like, like in this implementation, you would want to know, like, is this machine actually busy or is it not? Which means you would need to know some about what it's doing, like, because maybe it's hard to tell it from a black box point of view, whether a virtual machine is just, kind of like in idle mode or whether it's like chunking away on some hard problem and needs lots of access to the CPU.
Right. Yeah. And that's going to go with just what the scheduling constraints are and just how you want that to work. So I'm not familiar enough with like all the various hypervisors and how they do scheduling and whatnot. Obviously, interrupts are pretty straightforward, and that becomes a pretty natural boundary from when something switches from one to another, right? Mm-hmm. But yeah, this is a really deep
for sure
topic, for sure. We could spend 50 episodes.
Right. And the point of Mobycast is not to teach people how to write hypervisors, but to like make people better software developers and make people sort of aware of the things that are useful to being a good back-end developer mostly. Yeah, so we want to get just to that level where it's like, oh, now I know this additional thing that I can kind of have in the back of my mind as I'm writing code and knowing that it's going to run on a virtual machine or in a container, which we're about to get to in a couple episodes.
Cool, yeah, so maybe moving on with, so KVM, so again, it's, so 2000, this has been in mainline Linux since 2007, again, delivered as a kernel, a virtualization module in the Linux kernel. It takes advantage of hardware virtualization, so using the CPU virtualization extensions like Intel VT or AMD-V, but it also does support paravirtualization, using, there's a VirtIO, short for Virtual IO API. So for that hypercall API, for guest OSs that have been modified where you don't have the hardware virtualization support. Its basic architecture is, again, there's actually two main pieces. There's the kernel component, and then there's also a user space component. So the kernel component, there's a loadable kernel module called KVM-KO that provides the core virtualization infrastructure. And then there's processor specific modules for both Intel and AMD architectures that then leverage that core kernel module. And then for the user space component, it uses QEMU, which is short for Quick Emulator. And what this is a userland program that does hardware emulation, and it's used by KVM not for all the hardware emulation, but for the I/O emulations.
What did you just say? Userland?
Userland. Mm-hmm. So this is you'll hear about this in various different platforms. Like in Node, they talk about userland, and that basically ends up being like the NPM ecosystem, right? Of like users out there just writing modules that you can go and install. Okay. It's not part of the core, right? It's not part of Node core.
Got it.
And so the same thing with Linux, right? So Linux is, you have the Linux core with its kernel, but then stuff that's running in user mode and, basically applications, right? That's userland. And so QEMU is a userland program that does this hardware emulation. So that it's something that KVM leverages part of that, again, for the I/O emulation, it will do complete hardware emulation. QEMU stands alone by itself, and it's used by other hypervisors. But it's one of those things that when you look at KVM, you'll always see references to QEMU because it is using that for part of this.
Okay. And so one of the takeaways I got from what you just said was a bunch of information, but you essentially said KVM is built up from modules, and there's sort of a core module and then modules that are on top of that. And each of those modules have the ability to mix and match and give you different types of virtualization, from paravirtualization to complete emulation, full virtualization, and hardware virtualization.
Yeah, absolutely. And, another core takeaway to that is that it's Linux. Linux is definitely one of the most popular operating systems out there, especially in the cloud space. And this is something that is highly performant. It's relatively newish in that, it hit the main line in 2007 versus things like Zen, that grew out of, I believe, an academic project in the late 90s. Type time frame, right? So this is kind of a later stage hypervisor. Mm-hmm. It's core. It's built into Linux. It's got a lot of great support for just from a performance standpoint, with doing the having taken advantage of hardware virtualization. It's got the kernel support. It's leveraging other pieces for other operations that are less critical, like QEMU for the I/O emulations. And one of the reasons why we're talking about Hyper-V and KVM is because these are two of the most popular, most important hypervisors in the clouds, in the public cloud space, right? So obviously Microsoft Azure, Hyper-V is definitely going to be one of the core hypervisor using there. And then for AWS, they started off using Zen as the primary hypervisor for EC2 instances, and recently have been switching over to KVM as kind of like the next generation, right? And so that's why I thought it'd be good to talk about both Hyper-V and KVM, because they really are. These are some of the ones that you're going to hear about when you're talking about cloud native computing and virtual machines and what hypervisors are being used.
Mm-hmm. In your experience, does that ever really come up? Like, do you see it anywhere, say in the AWS console, or because that is the kind of thing that when you see something like this in the AWS console, or even in like an AWS certification exam, it's like, oh God, I don't know. I don't ever install type 1 hypervisors.
Yeah. So for the most part, no, right? And that's why we can all use the cloud, and we don't have to know exactly, we don't even know we don't really have to understand what the difference is between a virtual machine and a container, right? And we can still kind of use it.
Yeah.
But it is helpful. There are when spinning up EC2s, there are options like, do you want PV or do you want HVM, right? And so what that's saying is basically, are you going to be using paravirtualization, or are you going to be using hardware virtualization? And so
there we go. Yeah.
Those options have appeared in the console, and kind of understand what it is. Zen is something you will hear a lot. You'll see it in documentation. You'll hear people talking about it. And it's one of those things where it's like, okay, what does that, they said that word, but what does it mean? Well, hopefully this gives context to that. Like, okay, Zen was, it's one of the core hypervisors out there. It's the way that VMs get installed. And so we talk about things like EC2 instances. To us, when we use them, they feel like it's a machine, right? It's a server, but it's not. It's a VM. And so kind of understanding how did those things exist? What does it mean to spin up a VM? What's actually happening, and what technology is being used?
Right.
And so to talk about Zen and then KVM, and KVM, again, you're going to hear more and more about this going forward, especially in AWS land. Maybe that's what we can kind of talk about next, is just the AWS landscape and kind of what they've done there. And so kind of now take this concept of virtual machines. We said how important it is to the cloud, and how it really has enabled the cloud to exist. Well, the cloud obviously is growing tremendously, right? When AWS first launched back in, 2006 or whatever, how many virtual machines do they have? How many EC2 instances do they have? I don't know what the number is, but it's whatever the number is then versus now.
Definitely orders of magnitude.
Many, many orders of magnitude difference, right? And so, obviously they're going to be they've built more data centers, and they have more racks, and they have more physical servers that they've bought, but they need to get more and more performance out of each one of those. And they need to be able to run more and more virtual machines on a piece of hardware, right? In order to accommodate that kind of growth. So it's kind of interesting to take a quick look at just what AWS has done there. And so, the original EC2 technology, like we said, it ran on a highly customized version of Zen. So Zen was the hypervisor they used for spinning up these virtual machines. And they did have both para-virtualization and hardware virtualization capabilities there. They had some, special requirements, running in the public cloud and having to deal with things like multi-tenant computing, right? So they, how do you just security constraints, right?
Dealing with security and noisy neighbors, those two things.
So they had to, some of the changes they made there is they had to make sure that memory allocated to the guest OSs was scrubbed by the hypervisor when that guest OS was deallocated, right? So
boot up, read my memory. What was in there? What was in here?
Right. And then, so obviously the hypervisor, like that gives you, that's the point that you have access to everything, right? So pretty core, needs to be pretty secure. So they needed to make sure that the only people that had access to the hypervisors were actual AWS admins, and right? Like, and so a very, very few select subset of actually just their job of, maintaining and patching and updating hypervisors and whatnot. So during this process, as AWS is growing, they're finding, Zen had many limitations on just being able to keep up with the performance that they need out of it. And so had to decide, okay, how are we gonna do this? And so, one of the things to keep in mind is that, so the hypervisor, it does a lot of things. So a traditional hypervisor, it's protecting the physical hardware and the BIOS. It's virtualizing the CPU. It's virtualizing storage and networking. It's also doing management tasks. There's a lot of surface area that a traditional hypervisor is doing. And they looked at it and said, well, why don't we start splitting some of that stuff off and optimizing those subsections, if you will, of the hypervisor to get better performance. So they, one of the, starting in 2013 with the C3 instance family, they came out with their own custom chips for this to have a custom network interface for faster bandwidth and throughput on those VMs. So start breaking that apart. They're still running the traditional Zen hypervisor on top of Intel Xeons, but they started that process of breaking it up. The next instance family, the C4, they then continued to do that offloading. So network virtualization went to custom hardware with ASICs optimized for storage.
And this also goes back to something we talked about last week. I was like, oh, how do you get a hypervisor on the machine? Is that like do you stick a thumb drive in and boot from it, or do you put a disk in it that's already got it on there? And what you're telling me now is that for these couple of modules, for the network interface and for network virtualization, it's literally in the chip. It's already on there.
Yep.
That hypervisor.
Yep.
Or that part of the hypervisor.
Yep. Yeah. So just, saying like, hey, these things, we need more performance out of them, so we're going to have custom hardware to deal with it and to make it faster. And so that was the C4 family in 2015, and then in 2017 with now the C5 family, this is where they introduced Project Nitro. And so you may have heard about Project Nitro, pretty important from a technology standpoint for AWS. And so what it is this is like the completely rebuilt hypervisor where they've broken apart all the functions that the traditional hypervisor is doing, and they're offloading it to either dedicated hardware or dedicated software. This is also where they replace Zen with KVM. And so Project Nitro is now using a highly optimized KVM version that's tightly coupled with an ASIC. And so now they're seeing, incredibly fast performance for VMs approaching performance that you would get on bare metal.
It seems like black magic, and like you'd have to be, just the absolute, super genius to be able to do that. But as I sit here and think about it, it's like this it's maybe not so hard. Like, there probably exist programs that if you can get your, Linux library sort of organized correctly and, put together just right, there probably exist programs that can take modules or pieces of your program and basically turn it into 3D print for a chip, right? Like, you don't have to like build the program in the chip. You just take this KVM. It was already open source. You break it apart. You reorganize it just so that it'll fit into this, program that you're writing. And then the output of it is like an instruction set that tells some big machine that makes ASICs how to make your ASIC. Like, you know what I mean? Like, this is all built. And this is something we talk a lot about, is like all this super hardcore stuff. That seems absolutely impossible is totally possible because it's all like layers and layers and layers of tech that have been built up to make it doable and easy.
Mm-hmm. Yeah, I mean, the thing that I've just come to appreciate, because like when you think of these things in and of themselves, it seems like, it's black magic. It's incredibly difficult. Like, how would you ever do that? Mm-hmm. Something as silly as like a dishwasher, right? And having like timer functions on it and different, settings and maybe it's connected to, other appliances or whatnot. But that wasn't developed in a vacuum, right? That's an iteration over the previous generation, which is an iteration over that. So everything, you're always building on top of something, and you're always, just building on top of the previous layer. And so the same thing goes with software. It definitely goes with hardware. All that said, these cloud companies like Microsoft and Google and Amazon, they're not just software, they're hardware companies as well. So Amazon, they went out, they acquired chip companies, and I believe it's been several. So they actually have chip designers now as just part of the Amazon team. Mm-hmm. And I guarantee you the number of people working on Project Nitro, it wasn't a 2-pizza team only, right? This was hundreds and hundreds of people working it across all different disciplines, and some of the most fundamental experts in these particular areas working on it. So it is hard, but it's obviously it's doable,
right? And we're beating it to death, but I also want to add that it's not one person that understands like how to optimize the hypervisor and also how to optimize the layout of silicon on a chip. Like, no,
exactly,
yeah,
indeed. All right, well, that is our whirlwind tour of hypervisor implementation. So hopefully that helps illuminate some of the questions that we had last time. It's still a pretty deep topic. We could, like I said, go on for many more episodes trying to break all this stuff down. But hopefully these 2 episodes have given a really good fundamental understanding of like, okay, what is a virtual machine? What's going on? Mm-hmm. What is a hypervisor?
Yes.
What is its purpose? And how is all this stuff segmented and partitioned and protected, and what does it mean to have hardware virtualization versus para-virtualization? So
yes,
this will really set us up well as we go into the next few episodes to talk about containers and how are those different.
Yes. What I'm most excited about is that I think that after this series, there's going to be a bunch of talks that they do at reInvent that'll kind of open up for me and all of our listeners. Like, hearing about this stuff you just said, there's absolutely talks at reInvent that go in detail over some of this stuff. And if you walk in with the knowledge of just from these 4 episodes, you'll be ahead of the game, ahead of most of the people in the room, I would guess.
Absolutely. You could have a drinking game at reInvent. Every time they say Nitro, drink. It's going to happen, right? So right. 2019, yep. You'll hear Nitro a lot.
Well, very cool. Thanks so much for going over that, Chris, and I'm looking forward to continuing next week.
All right. Thanks, John. See you then.
Bye.
Nobody listens to podcast outros. Why are you still here? Oh, that's right. It's the outro song. Come talk to us at mobycast.fm or on Reddit at r/mobycast.